Okay, so the discussion has been about the algebraic properties of derivatives, functions of several variables, so the gradients, and the main one is actually the last one, the chain one, and now we want to use it in all of the not all of the properties, the main properties, and they just in this order. The last one is the channel, so we want to use it. And the main application is once again to study functions of several variables, specifically taking trips on the surface of its graph to see what's going on. And one of the things that I have alluded to many times, and that is if you go along the gradient, it is the direction of the fastest growth of the function. Okay, the gradient, that it is a vector, so at every location it will produce the fastest growth, which is what I have implied, but many times, I think I may have been using it a few times, but well, it is at some point we're going to prove it, and in that direction, to take that step in that direction, this is what we're gonna look at first, and that gradient as it relates to level curves. So we started here. So the conjecture was also, it may have come up earlier, is right here that they being the gradient of vector, and now we realize, and the level curves are perpendicular, but in a sense that is not entirely obvious. If you look at some of the kind of edge cases when the level curves are curves, so you have to be slightly careful about that, but fortunately we already know what to do with them. These level curves are to be traveled with a parametric curve. Okay, so whether it's curved or not, as you can see, it could be everything or nothing, or could be anything, literally. Yeah, so nothing, everything, anything, but ideally it is a curve. How to describe, under what circumstances it's exactly a curve is still to be discussed. But let's just take the simple case when we just take a parametric curve that goes through stays on the same level. Okay, so the function is constant. This is a very simple idea right here. Is that that parametric curve f has to be constant to stay on the level curve. Okay, so if that is a level curve is a curve, then we're good. So suppose we have a bunch of level curves. Okay, and then we just take a trip along it. So that's, by the way, there is nothing else we can say about the parametric curves. For example, they don't have a direction. Okay, parametric curves do. So that distinction might be important later. So these are level curves, and then I take a trip along one of them like this, and that is my f. X is equal to f of t. I could go slow, I could go fast. Ideally, I just don't want to stop because. Why? Because the problem then would be how do we compute if we were interested in angles, then if you stop there is no direction, and then there is no angle, and the direction is determined by, so it is a constant. So now we are interested in the angle of this and that. Okay, so and that is del f. Bunch of vectors. Okay, so we're looking at one level curve at a time. Okay, so these are level curves. So along this, how should I put it? F is constant along each of them. Different constant for different curves, and then we take the gradient. So these are vectors, and then we measure then the angle between these vectors and the curve. The parametric curve will be what? Between x equal f of t on one hand and the curve, so that's the parametric curve, and on the other hand, well, let's do it we're doing it anyway. We're doing it one point at a time. So we're picking. We're looking at it like this. So this is my curve, level curve, then we pick a point. Okay, so there's the point, let's say A. Okay, so this is del f at A, the gradient of the direction. So as you can see, that is in the middle is actually a dip. It's not a hill, it's a dip. Apparently, the way I did it by accident there. So the gradient moving away from it. Anyway, so that's the setup. This comes from F, what you were looking at. It comes from F entirely. Okay, now we have some kind of curve. We don't know anything about it just yet. So the curve looks like this. So this curve looks like this, possibly. So hypothetically, we have then say f of. So this is x equal f of t over here. Okay, and f of a lowercase is equal to a uppercase. So it reaches that blue point in the middle. Okay, and now suppose that's where these meet together, a bunch of vectors of the gradients, plus the curve. Okay, so then we need the angle between that curve and the gradient. So at x equal a, at t equal a, and del f of at a. Okay, so it is, what is the meaning between what is the meaning of the angle between a curve and a vector? As you can see that picture, look at it. We have a parametric curve and we have a vector. What's the meaning of, how do we find the angle? So you can speak of, I mean, if it is hard to answer right away, then you can ask yourself, we are talking about the angle, is the angle between once again the direction of x equal f of t at that point A, and once again that vector del f. Okay, so I restated it slightly so it might sound more familiar. So the direction of a parametric curve on one hand and this vector on the other hand. What's the meaning of their the angle between them? The curve and the vector. Okay, what's the meaning between of the? Okay, looking at portion from different direction. What angle between what and what angles make sense to you?
Between 0 and 90.
What? No, I mean, what entities make sense to you so that you can compute angles between them? What? Well, yeah. Well, the answer is a tangent. Yes, but I was trying to get to that in a more subtle way, and the answer is to that question is vectors. We know how to find directions or other angles between vectors. Okay, so which means that we cannot really speak of a curve as having a direction, but rather we have to replace it with the tangent vector to that curve in order to be able to compute angles. Okay, so this is not good, but I do this, and I add tangent vector to it. Then we have two vectors to be compared to each other, and the angle is computed with the dot product naturally. Okay, so then the angle makes sense. So that was I was aiming at. So then the more precisely, then I continue on to say is the angle between Okay, the direction of x equal f prime of t is the direction then, pretty much by definition, of the tangent vector, and which is what? A tangent vector of the curve is given by what?
The derivative of
by the derivative of that line. So it will be simply f prime of a. So that red over here is in fact f prime of a. Okay, so that a refers to the moment of time where it is located at the point a capital. Okay, so that is the direction on one hand, and on the other hand, and once again I keep repeating this, del f of a. Okay, so two vectors, not by coincidence, both of them are referring to the derivatives of these two functions. So the derivative of the original function of two variables on one hand, and that parametric curve unspecified on the other hand. Okay, so all right, so okay, so that's fine, and how we can certainly compute it if you have the function f and you have f uppercase parametric curve. We can compute the angle between them. So let me just, if you remember. So what is the, remember the formula for it? The angle between two vectors. These are vectors, just any two vectors.
It's cosine vector 1 dot product vector 2 over the magnitudes of the two.
That's right. So it's a bit long, and then doesn't. So the dot product in the numerator and the denominator we have the absolute values of the two, which I regret putting it here because we really don't care about this, because we remember what we were after. We're after the perpendicularity. We want to demonstrate that the angle is 90 degrees. That was our conjecture. Remember, these are the, well, not these, but these are the pictures. Okay, for the paraboloid of revolution. This is paraboloid of revolution with these level curves. And the circles, and in the plane over here, its level curves as straight lines. Okay, so our conjecture was the angle is 90 degrees. So we don't really care about the whole formula over here. What do we care about?
The dot product between the two vectors is 0.
Right. So we want to show then that this thing is 0. Okay, that's all. So the dot product of these two should be equal to 0, and then we could, if you can. So let me write it out. F prime of A. Let me flip the direction. So del f of A dot f capital prime of A is equal to 0. So that's what we want to demonstrate. And so the two derivatives are equal to each other, the dot product equal to 0. And so do you see how we can demonstrate that? We've seen these expressions just recently. One derivative, the other derivative, dot product of two derivatives. Remember seeing it yesterday?
So we want to show that the derivative of the composition is 0?
That's right. So we saw it in the chain rule. We saw the dot product of two derivatives in the chain rule. And then if we do apply the chain rule backwards, this is equal to what? It will be equal to the derivative of the composition, indeed. So it will be the composition of f, composition f at, hold on a second, it's not a del, it's just regular derivative. It's a, it produces, hold on a second, yeah, it produces regular function, so it will just prime of a. Okay, so this is the chain rule. By the chain rule, that byproduct the derivatives is equal to the derivative of the composition. Okay, so now the question is why? Why is it equal to 0? You want to review this setup? Look at the right there in the box.
Oh, it's constant. The
Yeah.
derivative of the constant is 0.
There you go. So the composition is constant because it stays on the level curve, so then its derivative will be 0. That's all there is. So let me repeat this. So since f stays on the level curve, so we have composition f of t a constant function. Then its derivative with respect to t is 0 for all t. Okay, so that's pretty much it. The only things that are missing here just caveats that we have to mention, that the functions have to be differentiable, and but that is all. With hold on a second, with the and the other caveat that I mentioned is that we do not want to allow f prime to be equal to 0 because then it will be equal to 0 no matter what del f equal to. So that then we will be unable to draw the conclusion that we want to draw. So then the theorem takes this form. So suppose x equal f of t is differentiable. A at t equal a. Okay, then z equal f of x. I don't want to stick to only two-dimensional case, so is differentiable at x equal a capital, which is f capital A. Okay, then we also require kind of separately that f prime of a is not equal to 0. How about I also require that del f was not equal to 0, just in case for some reason. I suspect maybe. So both of these should not be equal to 0 for us to be able to speak of the angle. Okay, so that makes sense. And then I just write what I've got here is that hold on a second. The condition then is suppose also x equal f of t is constant along no, it is constant. Yeah. F of t is constant on an interval that contains a open interval contains a. Then we have our perpendicularity, so it will be f prime of a is perpendicular to del f of a cap. Okay, so once again, a curve. In that sense, we have proven that it's perpendicular. It will be true for every parameter curve, so we can travel slow or fast. Doesn't matter. It will have so the tangent line will only vary in the magnitude as well as could turn in the opposite direction, but it won't matter. So this is what I'm talking about. So this is what it might look like. It might look to a point in the opposite direction. So this is f prime of a once again is equal to f of a, and this one is del f of a, and they are perpendicular, 90 degrees. Okay, so to connect it, at least early on, to the bigger idea of the direction of the gradient is the fastest growth of the function, the direction of the fastest growth of the function. You can see that if you have a bunch of curves, parameter curves, and they're truly not parameter curves, but they're level curves, and they're truly curves, just curved, not straight lines, then how do I ensure that I'm climbing the fastest? I want to say this was 100 and this is 200. So what do I do to climb the fastest? I want to get from 100 to 200 as fast as I can. How do I do it? I go 90 degrees. Okay. So that's at least an explanation of why this is the case. We expect this to happen. We need this a little bit more of a build-up in order to state this. Everything is pretty much, but we don't really quite ready to say that the fastest growth in a particular direction doesn't have a meaning just yet. We have the fastest growth in direction of x, in direction of y. And that's it. And now we have to talk about direction derivatives in order to make that statement precise. So we'll just keep it stay with this. Okay, so that reveals our a lot about functions and then their curves. So the statement is we only use the parameter curve in order to discover this property, but really it is, since it's worked for any parameter curve, so it really will not that important which one it is. They produce the same exact result. Okay, so so that's one application of the chain rule. So very nice. And I want to actually state a little bit more of that. Let me just state we had a bunch of properties. The sum rule, the constant multiple rule, the product rule, and the quotient rule, and then the chain rule. These 5. But really, you can turn it into 2. The product rule and the quotient rule are not really that important. They look impressive, and they really come from calculus 1, and where you got to use it a lot, but really they're not that important. The other 3 are important, but the first 2 can be combined together. So this is the constant multiple rule, and or rather, let me go chronologically. So the sum rule plus the constant multiple rule is called the linearity rule. So this is what it looks like. Del, I think I have to start using Greek letters because I'm running out of. And G. Okay, so if I have not the sum of 2 functions, but rather what is called linear combination. Have you heard this expression before? A linear combination. So then the derivative of a linear combination of 2 functions is equal to the linear combination of those functions. So that's one property that combines the first 2. And then secondly, the chain rule. Once again, let me write it out again. The main one that we care about. So it is f composition f capital prime is equal to del f dot product f prime. Okay, so this could be most of what we care about to apply in under normal circumstances about functions of several variables. So the chain rule we applied already once. Let's use the one that I promised to prove previously with the nothing but the sum rule or constant multiple rule. And that is the property, remember the property of anti-differentiation property, if you like. So the way I put it in words is that the two potential functions. No, they're the wrong way. If I'll just write it without words. So del f is equal. Del f is equal to del g, okay, then f minus g is constant, okay. Very familiar one, I could just as well write it with primes, and then it will look like calculus 1. So if the two functions have the same derivative, they differ by constant. It applies to functions of numerical functions such as this, and then functions of several variables, the derivative is gradient. So if they are equal to, here they are thinking words that have to be spoken in order to turn it into a precise statement, but let's keep it for a moment like this. So this is the goal I want to prove. And I'm wondering, so if you remember how this is proven in calculus 1. So the one that is in parentheses, it's totally in calculus 1. Remember how it is proven?
We consider a function h, which
Yeah.
is
Yeah.
I forget if it's the difference of f and g.
Yeah. Okay, and then
We know that the derivative of h is 0.
that's right. So h prime is equal to f minus g prime. This is the linearity property comes into play, and you have f prime minus g prime, and the whole thing is equal to 0. And then there is a tricky thing here is you have to demonstrate that then the next conclusion is that so h is what?
It's constant.
It's constant. Yeah. So that is also a separate theorem. Do you remember what we used to prove this theorem in calculus 1?
Is it the mean value?
Yeah, as a matter of fact, yes. It's constant, and you use the mean value theorem. So like this, h prime of some point c is equal to f of b, h of b minus h of a over b minus a, and that proves it. So if all the derivatives are equal to 0, then there is no difference between the values of the function. So that's the mean value theorem, and that's why differentiability is required. So we don't have this luxury. So I will just allude to this as a way to do it pretty much. I guess I should mention this more often, and it is that many properties, especially this, the first one, can be done coordinate-wise. Not coordinate-wise, variable-wise, one variable at a time. So if you have a function of two variables, you do one variable, and then you do the other variable separately. Okay, so then and then you can prove the linearity property that way, but not really the chain rule. The chain rule is way more complicated that way. Even though it turns out to be a very nice formula, but it's because the variables are mixed with each other. Then that's why just doing it one variable at a time doesn't work. But the linearity works, and that conclusion also works, because now I can just imagine that the whole thing is simply referring to one of the variables of my function, and then I prove that with respect to that variable, our function is constant. Okay, so half work done, then into the other variable. Once again, with respect to that variable, the function is constant, and once again, I conclude that I have a function that is constant in both x direction and y direction, so it is constant. It's not enough to have constant in one direction because you can have something like this, but 2 is enough. As far as the, you could still prove it from scratch, but okay. So let's just state it, the theorem appropriately with the caveats, and the caveats are you need differentiability. So you need differentiability. So we assume that f and g are differentiable to begin with, but where is differentiable on a disk. Okay, so open disk. So that you cannot. So you don't want to. It does not apply to. Well, it cannot possibly apply to just one point. All the discussion, including these rules, can be done, and it is done in one point at a time. Differentiability at one point. But here, the Linearity theorem implicitly requires the differentiability on the whole interval. Okay, so then you have to have differentiability with respect to one variable on an interval, and also differentiability with respect to the other variable also on an interval. So together they form a box or square. Well, maybe that's actually a better way to put it. Rather than speak of a disk, let me say it is differentiable on a box. Open box B. Okay, and then they're constant on B. So the difference between them is constant on that B. So that box could be naturally two-dimensional, square, rectangle, three-dimensional, actual box, and you can do it in every single dimension. The result will be the same. Okay, so that is, as you can see, the linearity property is useful to study functions of several variables. The chain rule too, they will come up later as well. But at this point, we're moving on to, not moving on, but rather moving backwards, and that is the gradient versus non-gradient vector field. So we're studying a little bit of vector fields as they stand alone. But let me refresh your memory first about partial differentiation. So we can differentiate with respect to x and y, fx of y, and then you, as we know, together these form the gradient of f. So it's a gradient of f. It is at every point a vector or a vector field. So at each x equal a. At each point it's a vector. That's what makes it a vector field. Okay. So great. So that's why, as you can see, the change in each of these is a function of several variables again. Okay. So then the question of gradient vector field, whether or not such a thing exists. So if we start, instead of starting with f, we're starting with this v, a vector field v over here, and then we ask ourselves, could we go backwards? Is there such an f which produced v? So that's like anti-differentiation. So this is differentiation, and this is anti-differentiation. You can call it integration. It's a little bit, it sounds funny. Anyway, but then, and we did solve that problem a couple of times, and on one occasion we discovered that, yes, it was. We found that function explicitly, so we pretty much set out the problem of finding f through, so fx is equal to, remember fx is equal to, say, what the vector was x, and fy is y. Okay, and then just solve it. We solved it under one occasion, but when we flipped we put it, what it was, y negative x, then the answer was no. Okay, so that is, and we were lucky to have been able to solve that problem explicitly because the functions were simple enough. Integration worked out, and then and secondly, the well, the algebra that the integration produced was also manageable. Generally speaking, there's a better way to answer yes or no. Okay, so surprisingly, actually, instead of integrating, you continue to differentiate. Okay, so xy, and then we have f of x, xx, f x, f xy, f yy. Okay, which is incidentally what we're looking at is, it is the derivative of v. This is the derivative of v. If that row of v was, those two functions of two variables was, in fact, so let's make it clear, n is equal to 2. It was a vector field, then if we differentiate each of its components, you will produce 4 functions, and that somehow these 4 functions produce the derivative of v, of that vector field circled in purple. Remember that the vector field is a vector at each point, and then it has 2 numbers, and that's why we speak of it as a vector. Now we have 4 numbers for each location. So might be tempting to think of that this is also a vector just of dimension 4, but it's not. I mentioned that yesterday. What is it? Those 4 numbers form what?
What was the question again? Sorry.
What do those 4 numbers form? And it is not a vector of dimension 4. I mentioned it, yes.
I know we said there's times when the middle of the two, they should be equal, right? Or they could be.
Yeah, I'm getting to that, but that's not the point. So that is actually what I was going to talk about, but I just want to stop for a moment and mention this. They form a matrix. It's not a vector, but a matrix, and very nicely put like this: fxx, fyy, and then fxy, fyy over here, fyx. Okay. So then the derivatives are matrices rather than vectors, generally speaking. So it just happens to matrix sometimes could consist of 1 column and looks like a vector, or it could consist of 1 row, once again a vector, looks like a vector, but they're really all matrices. So it's a matrix. It's we're not going to have any time for it, I'm afraid, but at least it's a little bit of a preview. So all derivatives are matrices. Okay, matrices that depend on locations though. Okay, so it's like a matrix field rather than a vector field, if you like. Anyway, but that's not the point. The point is indeed that these 2 are equal under certain circumstances, which, what does it do to our matrix? Not much, it just, the matrix is, as we say, is symmetric. So those 2 off-diagonal values are equal, that's all. So that's not a big deal. The fact that we have 3 rather than 4 derivatives, that doesn't really change a thing. If there's one place for each, it's still a 2 by 2 matrix. Okay, so the point is that, well, first let me state the theorem. It's called the Claro Theorem. Okay. So it says that if, well, you remember that these are called mixed derivatives, which have been have not been used. Remember that these 2 derivatives are used for concavity. So you use fx to determine the partial the sign of the partial derivative, which gives you the monotonicity in a particular direction. And then if you look at fxx, then it will give you all the concavity in that particular direction. Okay, and then the same with yy. So they are very helpful, but the middle ones are also appear, and they appear in the second derivative test, in fact, which was also skipped, which classify, just like in Calculus 1, classify extreme points. And how do they combine together? They combine together for this matrix. Okay, so that matrix will tell you the kind of extreme points you got. Okay, so just worth mentioning. But we're looking at something else right now. We're just looking at the true mixed partial derivatives rather than repeated partial derivatives. So we assume that they are continuous. So suppose fyx and fxy are continuous. Then they're equal. Okay. It sounds a little bit weird because you say that the function is continuous and you can only check it if you already have them and then you already know whether they're equal or not. So what's the point of this conclusion? Well, there is a point. It is we can actually predict whether or not the certain derivatives will be continuous. So what we're saying here is that a function is we can tell, look at the function and we know without actual differentiation we can tell whether or not this derivative will be continuous. Let's say a polynomial of x and y will always be differentiable infinitely many times and all the derivatives will be continuous. Okay, so that is the point. And then you conclude that they're equal. Okay, so all right. So suppose now, so how do we use it? We use it to classify the vector fields, separate them, gradient vector fields, which you see here on the picture, they look like this, and the rest of them. So if it is a gradient vector field, it fits into this picture, and we can, instead of going up as we did last time, finding f, instead of trying to find, so we want a vector field V, and we want to know, is it gradient or not? Okay, so instead of trying to find f such that del f is equal to V, as we did twice, instead what do? We differentiate. Differentiate the components of V. Okay? In a kind of mixed way. So suppose the components of V are, say, P and Q. Then, and the P refers to X, Q refers to Y. And then we differentiate them across. So we differentiate P with respect to Y and Q with respect to X. And the result should be the same. Okay, let me show that just with those two examples that we had, how this works out. So V is equal to XY. So if P is equal to X, functions of two variables, Q is equal to Y, I differentiate P sub Y is equal to 0, Q sub X is equal to 0, so equal. So the conclusion then, this is it passes the test. It passes the test at least, and so it's a pass. I don't want to say that just we conclude that it is a gradient vector field just yet, but at least we say that there is no contradiction with the Claro Theorem. Okay, and then the other one was y negative x. Okay, so P is equal to Y, Q is equal to negative X. Now I differentiate, as you can see, I differentiate in a cross way. So P sub Y is equal to 1, and Q sub X is equal to negative 1. Not equal. Okay, so they cannot be. So they, being P and Q, cannot be the partial derivatives of some function. Some function f of two variables. Because if they were, we would be in that position over there, and we could differentiate one more time, and the mixed derivative is supposed to be equal to each Okay, so very easily we have proven that this is not the case. So the drawback is if we have a path and we want to find the gradient, then we have to start over. But at least we are easily can discard some of the theorems, some of the vector fields that are clearly not don't pass it. Okay, so let me state this in the form of a theorem. So suppose in dimension 2, the vector field PQ is a differentiable vector field. And let me write this way: dp dy and dq dx are continuous. Now suppose V is a gradient vector field. Then these two are equal to each other. dp dy is equal to dq dx. Okay? So that's a nice result based on a theorem that is not really that hard to prove, and it's kind of a, I'd say, I'm not sure how convincing it seems that two mixed derivatives are equal to each other. But at least it's not entirely goes against intuition. And then this way we can classify vector fields, but it is also fully applicable to functions, to vector fields of higher dimensions, because we're still doing two at a time. We're still doing two at a time. So you have three variables. You just differentiate with respect to x and y, compare them, then differentiate with respect to x and z and compare them. Differentiate with respect to y and z and compare them. Okay, so we'll do that next time.